Good afternoon, everyone. Uh, today we'll discuss about, okay, today is the final class of our difference equation. Okay. Uh, so far you have learned about uh, what is different equation and then linear different equation, right? And then first order different equation, second order and system, and then non-linear difference equation, right? And for each of these different equations, you also learn about how to do solution, okay, except for the nonlinear, okay, and then how to compute equilibrium, and then the stability of this equilibrium, okay. So, and today we will apply, okay, this different equation in the space and time, okay, so that you can see visually. Okay, so for this we can use Excel, or if you want to use Python, I can give you the link. I can try. I don't know. I'm trying this. I'm not sure if this works. You can try. Okay. And for the 2D, I'll explain later using Excel. Okay. So for the 1D, if you use Excel, like what I did, it will become quite long to code. Okay, so for this one, you just copy and paste. Okay, let me start with what is CA.
Okay. Sir.
Yes.
Sorry, your voice is a little bit small. Sounds a little bit muffled.
Okay, wait. Where to get that? Let me check. How to change the setting. Before we can open the setting, but now no more. Oh, there. Okay. Setting. How about like this? Is it okay now? Or still the same?
Still the same. It's okay. I can still hear you, but it's just a bit tiny.
Oh, there's a lag. Test. I think. How about this? Can you hear me? No? You cannot hear me.
Right.
Okay, so everything is auto, so I don't know how to make it better. Okay, let me continue in that case. Where are we? Okay, so this is difference equation, okay, where you put time in the row and space in the column. Okay, so let me share you the whole screen so that you can see. So this one. This one I zoom in, so let me zoom out so that you can see. So this is an Excel, right? The usual Excel, okay. So the only difference is now I zoom become only 20 something percent, okay, so that you can see the whole thing. Okay, so one cell is like this. Okay, and so I have practically I have many cell here. Okay, and I reformat it, and then each row here, okay, down here represent the down represent the time, okay? And then the row, the columns in one row represent the space. Okay, so okay, let's start. So what is CA? Okay, Cellular Automaton is or Cellular Automata in plural. Okay, is basically difference equation, yeah, in space and time. Okay, so it's a discrete dynamical system, okay, whose local behavior is completely specified in terms of local relation. So in my own definition, so that easier, so automata is just a program or mathematical method, okay, that can be presented in dynamic and spatial way. Okay, so this one is the characteristic. One, it has discrete cells, okay, and then it has also discrete time step. Okay, and then there are rules that control these cells. Okay, the value of the cells, and then that rules depends on the neighborhood of the cell. Okay, so basically you have learned about this, right? Discrete dynamical system or difference equation, right? So this one is the first order, right? So linear, okay, non-homogeneous, right? This one is what? This is the first order, right? The order is based on the K, non-linear because this is quadratic, okay? Non-homogeneous means there is some force here, okay, and so on. So if you look at this value of yk here, okay, k is discrete but yk is continuous, right? Okay, real number, correct? But in cellular automata, okay, that k is discrete and then the yk is also discrete, integer number. Okay, so the time discrete, the state value also discrete. Yeah. So this is just a special type of dynamical system. The one that we practice today in here is instead of discrete, we even put it even less than discrete. It is binary. Okay. But cellular automata itself is discrete value, not necessarily binary. Okay. Of course, we can also create a continuous value for cellular automata, but that's approximation. Okay. So it's a very simple virtual machine, okay, that will result a complex behavior. Okay, so let's call the discrete space as cell. Okay, so we call it cell. It's a side of a string of 1 or 0, so it's just bit string. Okay, so the simplest CA is only two states of 1 or 0. Okay, now the state of a cell at the next time step is determined by its current state, okay, at current time, and then by the state of its neighbor. So when we say neighbor, let me draw. So suppose this is your cell. Okay, suppose this is your current cell. So the neighbor means the left and right. Right? This is the left neighbor and the right neighbor. So this is left one, right one. Sometimes your neighbor can be not just left one, can be left two, yeah, right, or right two, and 3 and 4 and so on. So your neighbor is basically anything that is left and right of the current cell. Yeah? This is our current cell. Clear, yeah? What's the meaning of neighbor? Right. So the space is uniform grid. Okay. So basically, we call it cell because it's just like a cell. Okay, containing a few bits of data. Okay, and then the time advanced in discrete, and then each spatial cell, okay, its space contains state value. Now, the state value not necessarily discrete actually, yeah, can be number, continuous value. For example, 2.3, 7.5, that's allowed. Okay. Now, the rule of the universe expressed by a single recipe. So the whole things have only one set of rules, yeah? Not necessarily one rule, but set of rules. So that set of rule can be represented as lookup table. Okay, so based on that lookup table, you can check what is the next step. What is the value of the next the cell in the next time step? Okay, so this is important. The system law are local and uniform. Okay, so what is the meaning of local? Local means that to know what will happen here in this cell at a moment depends on the state of things near here, which is only within the neighborhood. Local means within the neighborhood. Okay, so if it is a graph, okay, local mean say this is another one. So if you are in here, local mean only this and this one. Okay, so the next is not included. Yeah, this one is not included. So only local mean the immediate neighbor. Okay, so action at distance is not permitted. Next, what is the meaning of uniform? Uniform means the rule are the same anywhere at any time. So this is like universal rule. So the law is applied for any citizens at any time. Okay. So the computation is mostly, yeah, not necessarily, but mostly in parallel. Yeah? So parallel processing. So the event is updating on a single cell, okay, and then its cell is one state variable. Okay. Now we should simulate millions of events in parallel to get the satisfactory experiment. Okay. Now don't forget the immediate adjacent processing element to the center is called neighborhood of that processing element. Yeah. Okay. Now here is the three characteristics of CA. Okay. So the individual cell is updated in parallel. Okay. Now its new cell value depends only on the old value. So yt plus 1 equal to yt, okay, and then dot here with the neighbor of the yt. Yeah? So neighbor of the yt. Okay. So the dot here represent any operation, okay, that you can define based on the rule. Okay. So it's not multiplication, this is dot of any operation. So all cells are updated using the same rule. Yeah? The n here represents the neighbor. Yeah? Clear? So this is more general than the somewhat more general than the difference equation because of this operation is undefined. Right? So you need to define that. So this is kind of family. Now, in the boundary, right? So suppose this is your cell. Okay. How about in here? This one have no neighbor, right? Right. So you can set any value, okay, as the fictive neighbor here, or you can set a torus grid. That means this one is equal to this one. So as if they are making a circular grid. Yeah. Clear? Torus grid means a circular grid. Yeah. Now, let's try, okay? Let's try so that you can understand the CA with only 3 cells. Okay, so you have only 3 cells. Okay, so let's call this C, this is L, this is R. Okay, so the rule is, let's define this. Yeah? The rule let's define as maximum of L and R plus C minus minimum of LCR. Okay, initial value is 1, 2, 3. Or what will be the next 20 values? Okay, so you can create the Excel for that. Yeah. So you see here. Okay, so I can create Excel like this. So let's assume torus boundary. That means left equal to right, right equal to left, right? So initially you have 1, 2, 3 at time 0, right? And then these are the rule. Yeah? So maximum of what? E in the left, and then C is the right of this cell, right? And then plus the center, which is itself, okay? And then the minimum of the 3. Yeah? Can you make it? Can you make it? So this is supposed to be simple enough. So let me make a new one. So I have T here, example. This is the time, yeah? Right? So, and then you have only left, center, and right. Right? Initially you have 1, 2, 3, is that correct? Okay, so, and because you want to make it torus, right? So in this case, here become right, and here become left, right? So, okay, and then now what is this? So right means I will put right here, and then left here I will put the left here, right? And then what is the rule again? Maximum of left and right. Okay, so this is talking about the center. So you take the equal maximum of left and right, and then plus or minus, plus C minus min. So plus the center, previous center, okay, and then minus the minimum of the 3. So we are talking about the center here. So once you make that, what you will do, you copy here. Okay, but here you copy this one. Yeah? This one is the copy of the right, and then this one is the copy of the left, right? So once you make this, what you will do, okay, this is time 0, this is just time plus 1, right? So then what you will do, you just copy it down, yeah, finish. There. Is it clear or not? Okay. And then the one that you show is only this one. Okay, so I can put this conditional formatting. Where should I put? Okay, so the conditional formatting, I'm supposed to make it per row. Right, I'm supposed to make it per row. There. Anyway. So what do you think? Now, to apply this in real world, okay, you set up the rule, your own rule. Okay. Oh, so far, is there any question? Did you make it? Were you able to make it?
Sir, LCR stands for
Left, center.
central right. Okay. But then for the space, it can be more than 3, right?
Oh, of course, of course. This is just
Okay.
this is
Example. Okay, okay.
just the beginning.
Then,
So
then the name will be not it will be not LCR again.
no,
It
no,
will
no. The
expand.
name is just number. Is better.
Okay. So LCR is just to
Yeah,
as an
just gives
example.
increasement. Yes.
Okay, okay.
Good, good that you asked that.
I'm a bit confused. So cellular automata is an abstract concept.
Well, okay. So I will tell you a story. Okay, there's a guy named Wolfram. Do you know this guy?
Wolfram Alpha guy.
Correct, correct,
Oh, the one who made Wolfram Alpha?
correct.
Oh,
Okay.
okay.
So Stephen Wolfram, okay, uh, is one of the genius in this century, of this century or last century. So he's still alive. Okay. So in 16 years old, he already got a PhD in theoretical physics from the University of Berkeley, yeah, UC Berkeley. So 16 years old, PhD in theoretical physics. Okay, and then uh, he developed Mathematica software. Okay, and he become one of the billionaire because of that software. Okay, and then of course he during his PhD he studied Cellular Automata. Okay, and then after he become billionaire, okay, so what he did, he stopped working and he only studied Cellular Automata for 10 years. And he produced one book, okay, NKS, New Kind of Science. So I in 2001, I asked my wife to buy that book in New York when they start launching it. Okay, it's just very thick book like this, $50. I think the Petra Library also has one, so you can check. Okay, and that one whole book, more than 1,200 pages, is just talking about cell automata. Okay, and he argued that in that book, okay, that cell automata is basically it's like a computer. It's a kind of machine. Okay, so in which you can do anything because it's computer, right? So uh, in fact, you can even create a Turing machine. Okay? That's in computer science we talk what Turing machine mean. It's a universal Turing machine. That computer in the beginning, computer is basically just a concept of what is computer. Right? So imagine that this guy, okay, spending 10 years his life, okay, to not do anything, just study Cellular Automata. Okay. Of course, after he become billionaire, but at the same time, that means he knows that this is actually very important. Right. And of course, before him and after him also, there are many research about Cellular Automata. Yeah. So I got several grants on this research when I was in Japan. So I developed Eden model to simulate urban growth, yeah? How the city growth, for example, okay, using Cellular Automata. I also did for my PhD, okay, also for pedestrian simulation using Cellular Automata also, yeah? And many others. Yeah. Later I will discuss some interesting model. Okay, and you can see there are many complex systems, okay, out of this very simple, right? It's just even binary one is rather simple, but it's creating some complex behavior. Okay, okay, let's continue. So the one that you use is machine Wolfram Alpha, right? That automatically compute your differential equation or your integration, right? Okay, that is from Stephen Wolfram. Okay, and he is the one who we talk about in this slide. In fact, yeah. Okay, so let's talk about very simple one. Yes, very simple CA. Okay, one dimension binary with one left and one right. Okay, so what will happen if you have each cell only binary, right? Meaning only two value, right? Either 0 or 1. So in that case, because you have three cells, right? The only possible value are 8, right? Correct, right? 2 exponent 3 is 8, right? So in that case, on the these are the only possible rules. Okay, you have only how many? Because you have 8, so 2 exponent to the 8, right? So in that case, 256 rule only. Simple, right? Okay. So, okay. In that case, you can state it this way. Yeah? The left state of the cell now. Okay. The right, because it's a rule, right? So it's a you have only 8 rule for each set of this 256, right? So on the left side, you have only these are the possible rules, right? 111, 110, 101, and so on until 000, right? And then on the right side, you have the next state of the cell. What I mean by the next state of the cell is the center. Okay, so these are example of the center that we can set. Of course, because there are only 256 rules, then you can set as either 0, 1, 2, 3 until 256. Right? So let's take example here. Okay, look at this. These are the rule. This is the lookup table. Okay, so say here, this is time 0. Okay, so and then what you will do, you check here, 0, 1, 0. You see this? Every 3 you take, yeah? 0, 1, 0. Okay, and then you go back to this 0, 1, where is 0? 0, 1, 0, yeah, rule 6, isn't it? So if you find 0, 1, 0, what you will do, replace the center 1 into 0. So there, replace the center 1 into 0. Clear? And then you go to the next one, 1, 0, 0. Can you see? This one, 1, 0, 0, okay? And then you go to the rule here, 1, 0, 0, what is this one? 1, 0, 0 become 1. So that means you replace this 0 into 1. There you see, 1, 0, 0, this 0 replace into 1, and so on. Clear or not? Should I demonstrate it? Or is it clear already? Livy? No.
I'm still confused.
Okay, still thinking. Okay. Uh, on the top here, okay, so here I could, this is the rule, 8 rules, right? So I'll put it this way, okay? These are the rules. This is the before and this is after. Okay, so the top immediate neighbor like this is the possible cell color combination of its immediate neighbor. So there are only 8 possible, right? Black, 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 white, and up to white, white, white. These are the only 8 possible values because binary, remember, and we have only 3 neighborhood, yeah, 3 cell in one neighbor, right? So then the bottom here is the color of the next center cell in the next step, in the next time step. Okay, is it clear or not? And then what you will do is for each tree you replace the center. So this one plug into plug, plug into plug. This is white into plug. Yeah, this is white into white. Only the center that you change. Okay. So okay, let me give example here with this rule so that you can see. Okay. Let me draw. Say what is your t equal 1. Okay, so I have only this cell. Oh, any number that you want to put. Can you put any number here? 0, 1, 1, 0, 1. Okay? Okay. So let's forget about the boundary. So t equal to, okay, so let's make a different color so that we can see. So I check here 0, 0, 0, 1, 1, right? Which rule contain 0, 1, 1 in the left side? 0, 1, 1. Which rule?
Rule 5.
Correct. Rule 5 have 0, 1. Okay, and then what we will do with that? The center 1 become 1, so still 1 in here. Clear, yeah? And then you go to the next one with this one. Okay, 1, 1, 0. Okay, let me throw in green so that you will see. So this one, 1, 1, 0. So which rule on the left hand side have 1, 1, 0?
2.
Rule 2, okay. In rule 2, 1, 1, 0 become, the 1 still become 1. So 1 again here. Okay. Next, what you will do, okay, let's go to this one. Yellow, I'll put yellow here. I hope you can see. So 1, 0, 1. So which rule is 1, 0, 1?
3.
Oh, rule 3, right? So the 0 will become 0. Still 0 here. Okay, so the boundary is special. So now you need to tell. Now depends on the boundary condition, right? So say you want to make it torus. Yeah? If you want to make it torus, what will you do? So if you make it torus, this one will become 1 and this one will become 0, right? Correct? So in that case, in, oh, what happened? again, you will put 101, so 101 with this one, rule 3 again. So this will become 0. And here, if you extend this one more cell, so 0, 1, 0, 0, 1, 0, rule 6. So you get the next step, it is 0, 1, 1, 0, 0.
So the rule will be the lookup table then.
Correct, correct. And
Then we just change the center part.
yes. Okay,
Okay.
add again the here, and then you can use the rule lookup table again. You see that actually, even manually you can do. Right.
Oh, so the function of cell automata is for what, sir? Like for is it to retrieve information quickly or
No,
like?
no. It's just in the beginning. It's just like in this case, yeah. In the beginning, is pure science, meaning pure curiosity.
Oh, okay.
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 Okay. You're okay. I understand the engineering background that you have. Right. You always think about how to apply things. Correct. So all this question. So always asking what is the application of this. Okay. So when I ask the scientist what is the application of certain things, okay, for example, muon or neon in the sky right now, we don't know what is the application of that at this point. And then say he will say, look, when Newton invented calculus 200 years ago, nobody knows what is the purpose of Newton law and calculus. Right? It's pure curiosity. Okay? But at the same time, who will know that 200 years later we can invent rocket, we can invent airplane, okay? All based on Newton law, and even automobile. So all actually based on Newton law. So the same thing here. So at this point, there are a lot already of application of cellular automata. Okay, you can search in Google. So the one that I presented here is purely out of curiosity. Okay, that we can find certain pattern out of these numbers. Okay, so because we have, you see here in the next rule, right? In the next rule is basically you have only 256 possibility, correct? So we have, so this Wolfram is the Stephen Wolfram. Okay? So suggest to use the binary value. Okay? So that means you have rule number 1, rule number 2 until rule number 255. Yeah? Or rule number 0, of course, 0, 0, 0. Okay? So how do you get that? Okay, so from the bottom, from black to white, from black to white. So we make it this way. In this case, for my case, I put it from the bottom up. Okay, so black here, okay, 1, and white means 0. So in this case, I have this say a rule. Okay, that means 250. Can you see where I get 250? Right? So from black, okay, this is 1, right? And then this is 1, this is another 1, 1, 1, and then 0, 1, 0. Yeah. So that is the binary number. So you convert it to decimal, you get 250. Clear? So okay. So how about this? Okay, what is the rule number of this pattern? Okay, so again, you look at the bottom. Okay, so right means 0. So you get 0, 0, 0, 1, 1, 1, 1, 0. So what is that? Okay. So that is 30, right? Or in Excel, cat. So say you have
Oh, 30 is from the binary number if we convert it into numerical.
correct,
Oh,
correct.
okay, okay. I was like, where do we get 30? Okay, okay, yeah.
Okay, so you know this is one 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 zero, right? So this means multiply by 1. This one is multiplied by 2. This one is multiplied by 4, multiplied by 8, multiplied by 16, isn't it? Right, so 16 times 1, 8 times 0, 1, 8, 4 times 1, 2 times 1, 1 times 0. And then you add all together, you get 30. Okay, so this is rule number 30. Clear, clear. So of course, if you I said, okay, can you give me a rule number 30? You will get this part. Okay. Vivi, is it clear or not?
Yeah, it's clear.
Good, good. Okay, so next. So okay, practice. Okay, what is the rule number?
Whites are 0, right?
Yeah, white is so you can put 1, 0, 1, 1, 0, 1, 0. Okay, so this one 1, 2, 4, 8, 16, 32, what 64. Yeah, in here is 128. Yeah? So 128 times 0. So then you have what is this? 64 plus 16
16.
plus 8, right? Plus 2, right? Okay, so equal. You can come.
90?
Is that 90? Oh, yes.
Yeah.
So, and then if we ask, can you draw the rule pattern of rule 90? Yes, this one. Okay, clear? Okay, so when you want to simulate the 3DCA, okay, you start from one initial cell or many, basically in time 0. You can randomize or you can start with single cell. Okay, and then you can apply rules uh, to all cells, yeah, uniformly. Okay, and then each column represent the cell. Okay, and then show the result at one row below. Each row represent the time. Yeah. So this drawing is called time space time actually. Yeah. So say now I make it. So if you want, you can just make using Python. Okay, I make it in Excel. So rule 254. Let me check this one. So this one actually you can also make it on your own if you want. So it's basically checking if the boundary is the boundary torus or not, right? And then what is the initial value? So so if the initial value is 0, okay, then I will generate random number. Yeah? If not 0, then if that is the same as initial value, then become 1, otherwise 0. Okay. So that's it, right? And then the next one is the one that the real rule of CA, a little bit long. Yeah? Okay, so I use if then, if then, if then, if then, if then. Okay, that is depends on these 8 rules that we put. Yeah? If the left, okay, of this basically reading the lookup table. Okay? So the if then, if then, if then in here is representing the lookup table. Okay, and then one cell only, and then you copy to all. Okay, yeah. Okay, so I make it. So let's simulate that. Okay, so 254 we can check. So I have initial value at 90. That means cell number 90 here will be 1, otherwise all 0. Okay, and this here I put 254. Oh, you see the pattern? All plug like that. Okay, so exactly like this. Yeah? So, and if you look at this, okay, so the rule said a cell should be plugged. Okay, rule 254. If you look at the rule itself, okay, all cell must be plugged except when all its neighbor and itself is white. So that's why the pattern becomes like this. Yeah? Next, if you put rule 250, so we can simulate that. So I can change this to rule 250. Oh, I get the checker pattern, right? I get the checker pattern. So you see, I get the checker pattern, right? So this checker pattern is basically the same as in your nonlinear discrete difference equation. What is this? This is a cycle. Eh? Okay, there is a cycle here, right? So it's again simple pattern, okay, cyclical. Eh? Now there is a rule 90. So let's okay, rule 90 here. Oh, what is this? Oh, this is the pattern. Again, it's cyclical, right? Can you see? Yeah, even until down there, still cyclical, the same pattern. Okay. This is fractal, right? Yeah? So it's a cycle. Okay. Nested pattern. Yeah? It's not simple, it's fractal. Okay, but still regular. Yeah? Next, here is what is called complex pattern. Yeah? So let's check rule 90, 30. So put rule 30. Wow. So if you look at rule 30, now you can start to see on the left here, okay, you can see there are some a kind of simple pattern, right? But on the right side here, there are some, first it seems like a cycle, but it's not cycle, okay? It's kind of random. So it's a mixture between random and regular. So this is complex. This is what is called complex behavior. You see? So I simulate until very long, still the same okay, complex pattern. Okay. Next, if you check rule 73 here, okay, so let me check. row 73. Yes, so that's depend on the boundary. You can see I get again complex pattern. Yeah? Okay, so I can set boundary 0. Or 1. Okay. So you can see also there is some kind of regularity, right? You can see this column here of black, or red in this case, yeah? Column of red, right? And then there are certain other pattern which is random. So it's interesting to see that the combination of random, regular pattern, and a constant. Yeah? So it's a constant. Okay? So it's kind of complexity. And this one even rule 45. Okay, you get. See, I run rule 45. Right. So okay, let me put boundary 0. Okay, there is some regularity here, right, in the left side, and then in the middle is kind of irregular, so that means complex. And if you look at this very long, there is no apparent cycle or everything regular except this kind of complex behavior. Right? This is what is interesting. You can start to see the pattern. Yeah? And this is rule 1110. If you if you simulate this, let me put 1110. Okay. Again, there are a lot of 110. Oh, oh, this is kind of skin of the, what is this? The skin of snake or reptile, isn't it? There are some random pattern. Yeah. Depending on the boundary condition also, you can start to see. So if I put boundary 1, it will become like this. Okay, the pattern is totally different. So, but you can start to see there are some regularity, okay, some cyclical, but there is also some randomness inside, isn't it? So you may thought this one, for example, look at this. In the middle, you will think, oh, this one become regular, probably become all black in here, right? But after some time, you see, it will change. See? The pattern suddenly change here around this area. Yeah? The pattern is no longer a straight line. Okay. So again, it's a mix between regularity and irregularity. So this is what is called emerging behavior, self-organization. Okay. So the big question here is where the complexity comes from. Okay, so look at the rule that we set is really very simple, isn't it? It's just binary, only 256, right? And you may thought that, of course, if this is simple, the result must be simple, right? But and then the same initial condition with only single block cell, right? Again, the rule are simple, just interchange the role of red and white, yeah, on the left and right. So that complexity come from, yes.
Sir, can you please re-explain about the rule? I still don't get like what is the rule 30, rule 50?
Okay, okay, good that you asked. Uh, the rule, the rule that represent the lookup table.
Oh.
The rule represent the lookup table. You see here in the lookup table we have only 8 possible values, right? On the left hand side, you see in the left hand side here,
Mm-hmm.
and then this one, right? This is the left hand side, yeah, and then this is the right hand side. You understand this, right? This is the LHS. This is the right hand side. Yeah? This is LHS. This is the right hand side. Yeah? So from the left hand side to change to become right hand side. Yeah? So the rule, these are the rule, yeah, that you set on your own, right? But we know, okay, that the left hand side, because this is binary, right? So the left hand side does not change. There are only 8. There is no other 8, right?
Mm-hmm.
Only the right hand side can change. But look, because this is also binary, okay, and the left hand side is only 8, right? That means you are only have 2 exponent 8, right? That means you only have 256 possible rule, right?
Mm-hmm.
Here in this first row here, okay, this is the left hand side, right? The bottom here, okay, this is the right hand side, right, of the rule, isn't it? Is it clear?
Oh, yeah.
Okay, so that the left hand side does not change. That's always that. Okay? These 8 possible values of
Mm-hmm.
colors, 3 cells. Only the bottom, which is only the right hand side, can change. But remember, the right hand side itself is only binary. So in that case, you only have 256 rule, isn't it?
Yeah.
Correct? There is no other possibility. These are all possible values. Okay, so Wolfram said, okay, if only 256, I can keep name. Okay, because these are binary, so I can set based on this left hand side,
Mm-hmm.
standardize the left hand side into this way. Okay? Then the right hand side will be the name of the rule. Okay? The decimal number of the right hand side will be the name of the rule. Clear, yeah? So with that, you can say, for example, here, okay, how do you know the name? Easy, yeah? You know this is 1, 1, 1, 1, 1, 0, 1, 0, and then you put that binary into decimal, right?
Oh.
Clear? So that become the name, which is 250.
Mm.
Clear, yeah? When we said rule 250, that means equivalent to this drawing.
Ah, okay.
Okay, yeah. So when we said rule number, uh, what is this? This is rule number 30, represent this drawing. Is it clear now?
Okay, yeah.
Okay, yeah. So now if I have this rule number 30 and then you start with only single cell, what is the pattern, right? What is the time space diagram? Okay, so if I use rule number 254, I will get this very simple pattern. Okay. So you see this is the pattern of all black, right? Or all red in this case, yeah. So, and then if I use rule, what is this? 250, I will get the checker box. Right? So this pattern is repeating. Okay. And if I use rule 90 again, I get a repeating pattern. Yeah. So this is a kind of cycle, right? You have learned last time in nonlinear, okay, the possibility to get a cycle. So this is also nonlinear, the possibility of cycle. Okay, and here you can see this part is a kind of regular pattern. Okay, but this on the right side here is random. Yeah? We don't know, there is no cycle, right? And not regular, so it must be random here. Okay, but combining regular and random, so this is called complex. Okay, so if you look at this part, this is a kind of fixed point, right? Over time, it doesn't change. You see, in this cell, can you see that? Okay, first time is like straight black and white, black and white, and black and white, up to certain point, and then suddenly become a fixed point here. Okay, and this one is repeating pattern. Okay, but here is a kind of random, isn't it? You cannot see the visible pattern. Here is repeating pattern, right? And this is a fixed point. Because remember, this is time, yeah, down. And here is the space, yeah, on the each column, right? And in rule 45, is kind of random again. First regular, okay, and then suddenly become random. Okay, but when you see rule 1110, wow, it's not just random, it's become a pattern, look like real life, yeah? Skin of some kind of reptile. Okay, so this is what we call it complex, no? A mix of regularity and irregularity. Yeah? So that's why we said, look, how can, with a very simple rule like that, we can get this complexity. So emerging behavior or self-organization behavior actually is very interesting. For example, application, economy, our economy. Yeah? So Adam Smith said economy is like God hand, right? Meaning that there is some kind of rule that suddenly emerges that you cannot even change the price. Yeah. Yes, government can intervene with the price, but if you intervene too much, okay, your country will bankrupt. Okay, so eventually you need to study the economic based on emerging behavior or self-organization behavior, because economic is complex system. Okay. So game theory is also one of them. Okay. Of course, you study only the foundation of game theory. When you go deeper, you will start to see the complexity of decision making. Yeah? So then Wolfram said, look, I divide, okay, so he divided 4 types of CA behavior, yeah, in his paper. Okay, so number 1 is point attractor. So this is either a stable single point equilibrium or regular. Okay. You need to study the nonlinear video that probably you did not attend, Levi. So please check again. Yeah, we discussed about this last time. So second is about periodic attractor. Okay? There is a regular orbit between the K cycles. Yeah? And the third one is chaos, strange attractor. Okay? And then the last one, this is the one that is actually important, with this nature-like, yeah? With this complex system. So this is high information content, and sometimes we call this the edge of chaos. Why? Because this is between regularity and chaos. Yeah? So be careful, yeah. Edge of chaos is not chaos. Yeah? It's complex. Okay, so these are the example of the rules. So if you do in Python, so you can check on your own. Okay, these are the rules that I check. Okay, so a kind of repetition, right? This is point attractor, and these are called cyclic or nested structure. So there is a period attractor. So these are example of the rules. And then this is stress attractor, so randomness. So again, the rule 30, rule 45, rule 73, you can start to see kind of random, chaotic behavior. Yeah. So complex, non-repetitive with no apparent pattern. Okay. These are all chaotic rules, so I listed here. Okay, and you can see the examples of chaotic rules in CA. 1D CA, this is one of the simple CA. Okay, and these are example of complex. You see, I just reverse because it's too long. So rule 1110 is complex. So there is some kind of localized structure. There is a regularity, some time here, and then there are some randomness, irregularity. Okay, the same thing with these rules that I put here. So this rule 193, rule 110, rule 137, rule 124. You see all of that similar to nature. Yeah? Okay, interesting, right? So, and if you look at the history, okay, this is from the book of Wolfram, okay, the NKS, New Kind of Science. So if you look at the centuries, so over time, yeah, especially the different civilization, this is the Islamic art. You see, these are actually CA, right? You see, this is actually Cellular Automata that we can also develop similar pattern, right? So, oh, what is this? Okay. So if I have this input and I have that output, can you find the roll number and then what is the type? Yeah? Whether it is type 1, type 2, type 3, type 4. Type 1, type 2, type 3, type 4 is this straight attractor, complex, periodic, or fixed point. Yeah? So these are the 4 types. Is it possible? Is it clear or not? Yeah. Something that make you doubt, you can ask. Implementation is easy, right? You just copy and paste that code. You know? The point here is this is like the beginning. So okay. Now, of course, earlier we decide only binary, right? So only 0 and 1. Okay. So in the book of New Kind of Science, okay, he also tried ternary, so meaning 3 color. Okay, so that one he put it as Wolfram, black, gray, and white. So 0, 1, and 2. Of course, what is because ternary? So what is the total possible value? Become this is million, this is billion. I don't know what is this trillion. Right? So the possible values is trillion. Yeah? Just because you increase from binary to ternary. Okay. So this is the example of the rule 777 of ternary. And yeah, this code of ternary, okay, you can also see certain pattern based on that CA of 3 color, okay, 1 DCA. Okay, this is again code 1041 out of the 7 trillion. Okay, he simulated, and these are the pattern. Okay. Again, example. This one is interesting. So code 1599. Okay, he start from one cell here, okay, and then you start to see there are some random pattern and then some regularity, right? Okay, so you may thought that this one will go into some kind of similar mix between regularity and random. But after some times, okay, after 8,282 steps, okay, suddenly it all become just simple repetitive pattern. It doesn't change anymore. So this is what make it interesting. Okay, you don't know what is going to happen next. Right? And this Langton is one of the researcher in Santa Fe Institute. Okay, I asked you to join the Santa Fe Institute course, right? So he proposed, he called it lambda parameter based on the CA. Yeah? And he simulated only the logistic dynamical system that we discussed last time about bifurcation parameter mu. Okay, so we found that the parameter mu, higher the number, the behavior turn, right, from fixed point and then to periodic and then to chaos, right? So and then he said, okay, probably we can use that as parameter that we can use. Yeah? So what is this for CA? Let's compute the proportion of plug cell output to the total in the rule. So for example, rule 254, so the plug cell is 7 divided by the total, of course, 8, right? 250 is total plug cell is 1, 2, 3, and 6, right? These 2 are the white. So in that case, 6 over 8 and so on. Yeah? So if you have rule 30, this one is 4 cells as plug cell divided by total 8 and so on. So when will be the complex or chaotic happen? Yeah? So based on that Langton parameter, lambda parameter, yeah, it's not perfect actually, but gives some kind of prediction. Yeah? So if the lambda parameter is very low or very big, yeah, near 1 or near 8, that is fixed point. Okay? So in the middle is kind of periodic, okay? And then total emitter 0.5, okay, you will get about chaotic behavior. Of course, where is the complex? Complex is between periodic and chaotic here. So yeah, there are some people say that CA is actually a programmable computer. So in the book of NKS, okay, New Kind of Science. So Wolfram gave a open question. Okay, so all class of 4 CA can perform universal computation. That means it can be used as a program. So that is the big question here: is this possible that all complexity in nature are actually come from simple rules and simple initial condition? Next question is, are we actually just a program? Okay. Is life itself is just a simulation or a program? So that's the next question, right? So, right. So I will not give you assignment, okay? But if you want, you can just try on your own. Okay. So I will give you example Okay, so this is one of example of CA, okay, on social project. Okay, it's proposed by a guy named Schelling. Can you see my slide? Okay, so this is very simple application. And before Wolfram, yeah, this one is talking about in 1971. Okay, using simple cell automata, yeah, to understand the phenomena of racial segregation. So it's a kind of agent-based model, right? So now you divide the CA into two classes, actually three color in that case, yeah? Because you have the background color, and then you have agent 1 and agent 2. Yeah? You have two color agent. Okay, so you start to create agent based on CA. Okay? In fact, if you want to do a CA more using a multi-agent system, okay, you can download the program. I forgot the name. Loco, NetLoco. Yeah, you can download NetLoco. Search in Google. Yeah, NetLoco. You can download and you can play with it. Yeah, there are a lot of program. And if you join Santa Fe Institute, there is also a course about NetLoco. Okay, and to create a CA. Okay, agent base. Okay, so the agent base is useful to understand the relationship between individual decision and system. Yeah? So when we said complex systems, sometimes we try to understand how the microscopic level decision will influence the whole system as a whole. That is the usefulness of this CA. Okay, so for example, in economic, each individual are doing just buying and selling, right? Yeah. Micro level behavior is just buying and selling, so individual decision. But in the macro level, it becomes the economic. Okay? The same thing with your cell in your body, right? Each cell in your body is doing the job as a cell, but the whole things become your body. Suddenly, it has some kind of consciousness that you can do something. Okay, the micro level is your cell, but the macro level is actually you. Right? The same thing, everything in this life is actually can be zoom in and zoom out. Right? So, say the building. Okay, so this building, if you look at it as a building, yes, it is a building. But if you go into the detail, you will see the mixture between cement and the stone and the sand, right, and water make into concrete. Yeah? So on the detail, you can see the detail. Same thing with traffic. Yeah? In the road that you probably see the traffic congestion. Each of these micro level is individual decision of the driver, isn't it? Right? But on the macro level, you can see the traffic flow. Okay? So that you can see the traffic congestion, macro level. But in the micro level, it's actually individual decision. So that is how we can see how useful is CA in application. Okay? So in my model, it's, for example, in urban model, each cell represents the development. Okay? Individual will develop here or not. Okay? Will increase the depth, will buy this or not. And then later on, you can see that how the city grows in the macro level. Okay? So in pedestrian simulation, each individual will move only within the neighborhood. Right? But on the macro level, you can see them as a flow of movement. Okay, so I hope you understand the meaning of this macro level. Yeah. Is there any question? So the agent model, okay, intelligent behavior, okay, but only with a very simple set of rules. You decide the rule. Okay. If you want to apply, Okay, it is you who decide the rule. Okay, and the information to decide for each agent, the decision of each agent is only based on local information. Yeah? You can create random elements between this agent, okay, so that they can interact within the space. Okay, so Thomas Schelling, okay, probably one of the first on one of the most famous agent-based model, okay, to model what is called racial segregation. So in the US, okay, around 1960s, the, the black movement was very big at that time. Okay, so people were asking why the black and the white people are fighting each other, right? So then this person creating a model. Okay, so look, the agent in this model are not racist. Okay, okay, so but the outcome of the interaction, okay, it happened as if they were racist. So this try to explain that racism, okay, is come from the rule, okay, is not inherited within the race itself. Interesting, right? So okay, let's do this. Originally, of course, Schelling was not doing it in computer, so he just used a board. You can maybe use this as a board game using two type of coin here. So you give color. So say this is 2D. Okay. So initially I created random. Okay, I put pink and blue. Okay. Pink, its pink cell represent one agent. Okay. And then eventually, okay, it will become segregated. You see, eventually it will become segregated. Okay, let me run the simulation. So this is, can you see? Can you see this? Okay, so these are the code. I make it in MATLAB. So, okay, so I just set the maximum column 35, right? Okay, and move me. Yeah, it's just making it color. Okay, and these are the checking the neighborhood, right? For each agent. Yeah, M1 M is the matrix, right? And then checking the neighborhood for each agent. Let's see. Let's run first. Can you see the movement? Yeah. It started random, okay, and then it becomes segregated. Yeah. It started random and then it becomes segregated. Yeah. The same thing. So let me run again. So you see, it started random, okay, and then it's segregated, right? So that's the question is, yeah, to answer why there is a racial discrimination, okay, using the simple model of CA. Okay, so let me go into a little bit detail. Right, so the model is just grid. Okay, we one cell per one agent per cell. Okay, empty cell means unoccupied, and there are two types of agent. It is red and blue. Yeah. Initially, you can just set any number of blue and red, and then you can also put random location. Yeah? And then you set a threshold. Yeah? So this is the interesting part, is to set the threshold. Each agent has minimum required threshold for living with those of the same type. Yeah? So the agent will move if fewer than 3% of the neighbor are of the same type. Okay, so now the rule is this: when the number of the same type of the neighbor falls short of the agent threshold, then randomly relocate to the new spot of the board. So random relocation. Okay, so now even this is the result. Yeah? So even when the agent are Thoreland of the opposite type, okay, apparently the segregation still likely to emerge. Right? So this is emerging behavior. Okay. Now the segregation arises because of the phenomenon of what is called tipping. Oh, uh, there is a book, okay, called Tipping Point. Have you checked? Okay, let me check. I read that book a long time ago. Tipping Point. Oh, there, Tipping Point. Oh, Malcolm Gladwell. Okay, so if you have time, check this. Probably there is also in Wikipedia. Okay, tipping point, how little things can make big difference. Can you see? Okay, by Malcolm Gladwell. So this is there is an Indonesian version if you want also. So back here, okay, this phenomenon of tipping, okay, the early movement, even a few agents can create the incentive for other agent to move. So, and then it will become a cascade of movement. Okay. It will die out, the cascade of movement will die out only when the system becomes highly segregated. Okay. So, kind of domino effect, right? Cascade of movement, kind of domino effect. Okay. So, then of course, if you want to do scientifically, you start to ask questions. So, what is the parameter, right? And what kind of statistic to measure the degree of segregation and so on, right? So, yeah, these are the later you can go into the detail. Okay. So tipping is a process by which the movement of agent causes a cascade of further movement. So apparently, okay, this tipping point, okay, is something that is very important. Okay, there are a lot of physicists nowadays even create different model about this tipping point. So one of the example of model here, I try to, okay, is a model of avalanche. So let me run this. This is based on Burbach. This is the name of the author. So you can find the book. Yeah? The title is Self-Organized Critically. Can you see the simulation? So in this simulation, okay, it's just a pile of sand. Okay, in this simulation, it's just a pile of sand. So randomly we pour one type of grain of sand in this area in the middle, randomly. Okay, and if you look at this, okay, it will become supposed to be going up and up and up, right? But eventually, there's a kind of avalanche going on here, okay, just because of one grain of sand that we place randomly here. Okay, so that grain of sand that create a tipping point, that kind of avalanche. Okay, small input, okay, that will make a very big difference. That is the meaning of tipping point. Okay. Okay. So if you look at the simulation here, suddenly going up, 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 and then suddenly become fall down. Okay? It will fall down again. So that is the meaning of tipping point there. Okay. So is there any question about this? Yeah. So of course, if you want to do more, you can do more analysis about that tipping point and so on. So, but this is different version.
This is not in our Lantera, right, sir? This like
Really, this is not. Okay.
yeah, we have the 1D and 2D, but not this one.
Okay. Okay. I can add later.
Okay, thank you, sir.
Okay. So the CA I close. This one I close. Okay. So let's go to the 2D in that case. Yeah. The 2D CA so that you can also play with it. Can you see the slide of 2D? Okay, and I'm hoping you can creating very simple 2D CA in Excel. Yeah. Again, if you ask me what is the purpose, no purpose, just play. Okay. The application is up to you to decide. Okay, you create the rule, and then based on that rule that you create, then you interpret. Okay, and then you will create your own CA model. Okay, so let's talk about 2D CA. Okay, so an event is updating in a single cell. Okay, so each cell is just one variable, right? So we should simulate million of event, okay, to get satisfactory result. Okay, so you know when we set center, that is the computing element. Okay, and then the neighborhood here. Now because we are in 2D, okay, let's do it this way. Okay, 3 by 3. Okay, so based on the 3 by 3, okay, now we have two types of 3 by 3. Okay, so if you only have these all 8 neighbors, yeah, so that is the 8 immediate neighbors, right? So we call this more type. Yeah? This is the name of person. Now von Neumann, okay, the one that created game theory also, right? He used very simple, only four neighbors. So we call this north, south, west, and east. Okay, so the result will be different because of the type of neighbor that you use. Yeah? Only one type. Okay, so if you ask, oh, can I make it not 3 by 3 but 5 by 5 or 7 by 7? Yes, of course you can, right? So the definition of neighborhood, you are the one who define neighborhood. Okay, so let's make it simple, just 3 by 3. So neighborhood is just a kernel, basically. Okay, so you have a center here, right? When we set neighborhood, of course, it will exclude the kernel. When we set the kernel, that is the whole thing, 9, yeah, 3 by 3. The operation, okay, the cellular operation based on the cell ij, okay, and then you have a function that will transform the same cell into the next time step. The time step still discrete, okay? But now, because you are 3D and 2D, either you want to draw it in 3D or you can draw it in 2D. So in that case, you are no longer using space-time diagram. Okay. Instead, you are using simulation, okay, and animation. Okay. So, okay. Many operation. Okay, this is just introduction. Okay, so many operation in cellular automata, okay, is regarded as convolution. Okay, convolution of the signal with the kernel. Okay, so let me show you this way. So you have this is the signal, right? And this is difference equation. You see, this is t plus 1 and this is t. The only difference is now have space, yeah, with this ij. Okay, and then so I put an operation. This operation is called convolution operator, right? With certain kernel. Yeah? Okay. That kernel center at ij. Okay. If you want to abstract this. Yeah? Okay. When will you study AI?
Next semester.
Okay, so you will face this
Okay. You're the lecturer, right, for AI?
probably, yes. So
Okay.
okay, during image processing, you will learn this again. Okay. Okay, so in CA, okay, 2D CA again can be written as a lookup table. Okay, so say I use a von Neumann neighborhood like this. Okay, so at time t, this is at time t plus 1. Okay, what do you change? Again, what you change is only the center. Okay, is it clear or not? Okay, so if the state of cell is above on the right hand side, right, then become right hand side. So it's very simple string rewriting basically, right? If you found the left hand side, okay, rewrite it into the right hand side. So it's a rewriting simple rewriting system. Okay, and the one that you rewrite is not the everything; it's only the center. Clear? Now, say you use a von Neumann neighborhood, which only have 4 neighbors, right? So only the left, right, top, and bottom. So I call this north, yeah, south, west, and east. West, east, yeah. East is always in the right, right? So then you just fill up, okay, this value with 0 or 1, then you will get your rule, your own rule, yeah, if it is binary. Is it okay? Livy, is it clear or not? Huh? Sure, you can make your own rule, yeah. Joy? Okay. The left hand side, here is the left hand side, right? It's always like this, okay, for von Neumann neighborhood. Okay. The right hand side, you just put into 0 and 1. Okay, so instead of making that lookup table, which is complicated like that, okay, so my approach is a little bit different. So I use formula. Okay, I don't like lookup table. Why? Because I need to do if then, if then, if then, very long, right? This is only for neighborhood. If I have 8 neighborhood, meaning I need to do very long if then, if then, if then, right? So I don't like that. So I try to make it function. It is simpler. So using formula, in many cases, we don't need to type all this C new on the table, okay? But let's just do it using formula, okay? So example, the new one, okay, the new center, okay, depends on the old center, okay, and the neighbor, okay, and you don't even need to use all neighbor, yeah. So in this case, I use only the 4 neighbor, and then you create some kind of operation. Okay, so for example, I represent this operation as sum of mode 2. So, okay, so here are example of rules. Okay, so you can try on your own, okay, today if you want, okay, and the name here is just arbitrary, okay. So why? Because this one will create square, this one will create diamond, and so on. So this one is just any name. Okay. This one is the famous Conway life, yeah, artificial life. Okay, let's try majority and anil because this is like the simplest one. Uh, what is this? Sum 8 mean the sum of the 8 neighbor. Okay, sum 9 mean the kernel. Yeah, 3 by 3. Okay. What else? Yeah. C mean center. North mean the north, the top. Okay. East in the right. South down. West on the left. Okay. What else? Oh, that's it. Okay. So this is OR and AND. So you see here at the bottom here, sum 8 is just the neighbor, okay, and so on. Okay, let's try this into a real Excel. Okay, yeah, so you are using the new one, so you can just go to Excel option, okay, as the usual. Uh, Try to create the Excel iteration, you remember? So we enable iteration and then you set the maximum iteration to 1, yeah? Okay, and then we start to make a simple counter, right? And then using that simple counter you can create a counter, okay, and after that you can start to create the CA, okay. So to create the CA you just make say 20 by 20, yeah, or row and columns, and then you use conditional formatting, okay, and then of course you just press F9, right, to simulate. Okay. Okay, let's start with this simple. Okay, the rule is here. Okay, so let's try that. Okay, I will open Excel. Okay, so I open Excel. I share the whole screen. Okay, so what we will do, we will create basic, yeah, this is just random. Okay. Later we will use this random as start. So, okay, so to create a random, let's make a control first. So, control cell. So, stop. Right, so this is the yellow, and I call this control. Okay, and then let's make a counter. So, right, so let's put this 0. And then I go to, this is the most important step, is to go to the options, ins, right? Oh, not add in, sorry. Formula, enable iterative calculation, and then set this to 1. Yeah? And this still automatic. Okay, this one important, so can you do this one? This is to make into Excel iteration. Without this, it will not work. Don't forget, enable iterative calculation and then maximum is 1. That's it. And then click OK. Okay, and then you can start to create the counter. If okay, let me just control already. So if control is empty, right? Okay, and then this one itself plus 1, yeah? Otherwise 0. Okay. So let's call this counter, right? So this is, then I will say counter. Okay, so if control is empty, counter plus 1, otherwise 0. Right, let's test this one. Okay, so delete all. There it become counter, right? Okay, so stop. Okay, become 0. And then I will create a CA. So let me put 1 plus 1 so that I will know when is the 20. So let me get this up. Oh, too much. Okay, up to 20 only. Okay, it's up to you. If you don't want 20, you can create any number. Okay, so here I will put 1. This is just to show the row. Oh, still 18, so 2 more. Okay, so then here is my cell, right? So let me make this cell up to 20, right? So then the format, yeah. So say I make it the column weight into how much? 3? Oh, 3 is good. So if you don't like 3, you can change. So this is my area of games, yeah, of my board, okay, my board game. So if you want to see clearly, you can zoom in to see your CA. Maybe 3 is too big. Let me make it smaller. Make it 2.5. Okay, so this is better. Now, if you want to make it format, okay, let's create a rule here. Yeah? Let's make a rule, new rule. Okay, so then go here, format only cells that contain. Yeah? So can you see? So if the value is equal to 0, right? So what do you want to color? So I will fill that 0 with light green. Okay, so I will just put it into light green. Okay, so the same with the color of light green. Okay, the font the same as the fill. So just click OK. Okay, click OK. Okay, this is 0, so become light green, right? And then you select again, and then now we define 1. Okay, so you go to manage rule, you already have the light green, right? Okay. So then you create a new rule. Yeah? Okay. Again, if the cell contain equal to 1, right? What color you want? It's up to you. Yeah. Okay. Let's color it red. Okay. So let's color it this red. Okay. And the font again the same. Yeah? The font I color it the same red. Okay. Click OK. So I have two rules. Yeah. One is for 0, one is for 1. Yeah? Okay. So then apply this. Okay. So let's test. 1. Oh, that become black. Yeah. If you delete, become empty. Okay. So I have the board ready with the color. Okay. Is there any question? Can you make it? Just coloring. And let's start with the random, right? So how to create a random number here? So I put it this way, yeah? Integer of 2 times random. Okay? So let's do that. So this one is just integer of 2 times random. Okay. Oops. Okay, so I will go up to 20 here. There. Right. And then you can see I get 2 times random. Okay. Make it. So let's put some probability of random. Yeah, so I will set this 0.5 and yellow, or I will put it here because this is a parameter. Yeah? So let's call this threshold random, yeah? Empty. That we can set, right? So then, okay, I can put this if yeah, my random number. How to make a random number with threshold? Okay, I think I have the next slide. There. Okay, if random is less than the threshold 1, otherwise 0. Yeah? So that is the easier. So if I put if here, if my random number yeah, less than this threshold 1, otherwise 0. Okay, I use that and then I copy down. Oh, now what happened? Okay, if you run, it's the same thing. Yeah? You get the same random number. But now let's change this to 0.1. Suddenly becomes smaller. Huh? If you put into 0.9, of course, become full. Right? So now you can control the random number. Okay? So 0.25, I can control it. So 0.15, I can control the randomness. Okay, see, this is the basic first. This is not yet CA, right? This is just to create a random number. So up to here, is there any question? Can you make it first?
We only changed the formula on the column 1.
Only one cell that you need to change. Yeah?
Okay.
So
Okay, because I tried to change the whole thing and it just turned into one color.
Yeah, only one cell, and then you copy. You copy to all, eh? You copy to all.
Oh,
Yeah, the whole things.
okay.
You copy to all. Uh, do you have class after this or no?
Oh no. Oh yeah, we do. Wait. Sir, mine changed into a whole. It doesn't randomize.
Okay, you want to share your screen. If random less than random, one. Okay, and press F9. Okay, can I see the what is this called? Conditional formattings manage rule. Manage rule. Okay, so 7 to 27 F1. Oh, this is supposed to be okay. Okay, let's try first. Okay, close this. Just type 0, 1. You type 1. Oh, okay, so this is all become 1.
Yeah, it all has become one.
If your random is, where is the threshold random?
Just one.
If random number is less than threshold number, become 1.
Oh, the probability is also random.
No, this is not random. This is not random. This is number. This is correct. So can I see again? Cell. Oh, whatever. Okay, let me see the uh, formula and then trace dependent.
Formula and
Trace precedent. Press. Okay, that one. And then press F9.
oh, no, it's after.
Function F9.
Yeah, maybe it's because when I random the number is
Okay, and then okay. Maybe you need to put comma because you're formatting only.
oh, no, yeah. Yeah.
Okay,
So,
okay. It's
okay, that
your
makes sense.
okay. Okay.
Oh,
Okay.
yeah, that makes sense.
It makes sense. Okay. Okay, so we continue tomorrow in that case.
Okay. And we present tomorrow is OR, right? With 1 p.m. until 3, like now, like today.
It's up to you. It's up to you tomorrow what time you want because I have no other class that
Oh, okay.
except you.
Okay, okay.
So you want 3 hours, you can. You want morning, you want afternoon. It's up to you.
Okay. We can do like in the afternoon. Because if it too early, I'll
Mm.
like sleepy. Sleepy's gone. I'll update you in WhatsApp.
Okay, okay. So you tell me what you want.
Okay.
Continue this a little bit and then we can do the OR presentation and then I will finish the
Okay.
okay. So let's discuss over WhatsApp.
Okay. Thank you, sir.
Thank you.